Welcome to today's paper reading. Today's paper is titled, RankPrompt, Step-by-Step Comparisons Make Language Models Better Reasoners. This paper was published on the AR14 preprint by Qi Hu and colleagues from Northeastern University and Alibaba Group. Large language models, LLMs, have demonstrated significant capabilities in various reasoning tasks. However, even advanced models like ChatGPT can make logical errors. Existing solutions to improve accuracy, such as task-specific verifiers or voting systems, often require extensive human input or fail in scenarios with inconsistent responses. To tackle these issues, the authors introduce RankPrompt, a novel prompting method that allows LLMs to self-rank their responses without needing extra resources. RankPrompt works by breaking down the ranking process into a series of comparisons between different responses, utilizing the LLM's inherent ability to generate comparison chains as contextual examples. Experimental results across 11 arithmetic and common sense reasoning tasks indicate that RankPrompt significantly enhances the reasoning performance of models like ChatGPT and GPT-4, with improvements of up to 13%. Additionally, RankPrompt performs well in automatic evaluations for open-ended tasks, aligning with human judgment 74% of the time in the AlpacaEval dataset. This method also shows robustness to variations in response order and consistency, validating RankPrompt as an effective tool for obtaining high-quality feedback from language models. The research presented in this paper builds on previous work in mathematical problem-solving by Konsul-Kadziorsky et al., 2016, and Ling et al., 2017, as well as in question answering by Talmor et al., 2019, and Jiva et al., 2021. Recent advancements in large language models, LLMs, have shown significant promise in these areas. This paper aims to explore the capabilities and limitations of LLMs in enhancing both mathematical problem-solving and question-answering tasks. The focus is on understanding how these models can be further developed and applied to real-world scenarios, highlighting the need for continued research in this rapidly evolving field. In the field of large language models, LLMs, recent research has focused on their use as reasoners and evaluators. For reasoning tasks, chain of thought (COT) prompting has shown significant improvements by guiding LLMs to generate a sequence of reasoning steps. This approach is categorized into enhancing individual reasoning paths through prompt engineering and selecting the most effective reasoning path. However, these methods face challenges such as the need for careful prompt design and significant labeled data. On the other hand, LLMs have also been explored for evaluating and refining outputs, providing a cost-effective alternative to traditional crowd annotators. Yet, the design of effective prompts to elicit ranking abilities remains a challenge, often requiring substantial human effort. To address these issues, the RankPrompt method generates diverse reasoning paths and selects the optimal one through step-aware comparison, significantly reducing the need for labeled data and human intervention. Figure 1 provides a visual comparison of the direct scoring method and the novel RankPrompt approach. Direct scoring evaluates each candidate independently, assigning scores without considering the relative quality of reasoning paths. In contrast, RankPrompt employs a systematic, step-by-step comparative evaluation to rank candidates, enhancing the reasoning capabilities of language models, LLMs. The figure also highlights the use of comparison exemplars, which are automatically generated to guide the ranking process, reducing the need for manual intervention and labeled data. The RankPrompt framework is designed for reasoning tasks and operates in two stages. In the first stage, multiple diverse reasoning paths are generated, each potentially leading to a unique outcome. This is achieved using few-shot chain of thought, COT, prompting and temperature sampling to ensure diversity. The primary focus is on the second stage, where these reasoning paths are re-ranked by comparing their steps to select the optimal one as the final answer. This re-ranking process involves a comparative evaluation method that concatenates all candidate reasoning paths with the original question to form the ranking input. This input is processed by a ranking model guided by a step-aware comparison instruction. Additionally, to enhance the ranking capabilities of language model machines, LLMs, comparison exemplars are incorporated, which are generated automatically using a labeled dataset. Table 2 outlines the ranking template used in the RankPrompt method. This template instructs large language models, LLMs, to systematically compare candidate answers step by step, ensuring a thorough evaluation of each step's correctness and logical consistency. The output format is clearly defined, marked in red, to guide the model's ranking process. Additionally, the template incorporates comparison exemplars to enhance the ranking capabilities of LLMs, addressing issues such as irrelevant outputs and partial consideration of candidates. In this experiment, we evaluated GPT 3.5 Turbo across 8 reasoning tasks, which include arithmetic, common sense, and symbolic reasoning tasks. These tasks were conducted using datasets such as AQR80, ASDIV, GSM8K, SVAMP, ARC, Common Sense QA, Strategy QA, and the last letter concatenation task. We compared several methods including COT prompting, majority voting, direct scoring, zero ranking, and RankPrompt. The results indicate that RankPrompt significantly outperforms other methods, particularly in tasks like HUAR80, showing a 13% improvement over COT prompting. The Oracle results suggest that there is significant potential for further enhancements in ranking methods. Table 3 presents a detailed comparison of accuracy across 8 diverse reasoning tasks using the GPT 3.5 Turbo model. The tasks are categorized into arithmetic, common sense, and symbolic reasoning, each with specific datasets. The methods evaluated include COT prompting, majority voting, direct scoring, zero ranking, and RankPrompt. COT prompting employs greedy decoding at a temperature of 0, whereas other methods sample 5 candidates at a temperature of 0.7. The table highlights the best performance for each task in bold, showcasing the effectiveness of different methods in handling various reasoning challenges. Table 4 presents the test accuracy results on 3 challenging Big Bench Hard (BBH) tasks using GPT-4 over 5 candidates. The table compares the performance of different methods, highlighting the effectiveness of each approach in handling complex tasks. This data is crucial for understanding the capabilities and limitations of current methods in tackling difficult benchmarks. Table 5 presents the human agreements and associated costs on the test set of AlpacaEval when using GPT-4. The table highlights the average results of human annotators, denoted as interhuman, and compares these with the costs incurred by various methods. This data is crucial for understanding the alignment of automated evaluation methods with human judgment, and their economic feasibility. Figure 2 demonstrates that RankPrompt significantly outperforms majority voting, especially when candidate answers are inconsistent. The results, obtained from experiments on the HUAR dataset using GPT 3.5 Turbo, show that while both methods perform well with more than 3 consistent answers, RankPrompt maintains higher accuracy even when the number of consistent answers is less than 3. This highlights the effectiveness of RankPrompt in complex reasoning tasks where candidate answers vary. In this analysis, we focus on the factors influencing ranking performance. Specifically, we examine the impact of exemplars and candidate reasoning paths. The correctness of exemplars is crucial. Using incorrect exemplars degrades performance, especially in challenging tasks like AQR80. Conversely, correct exemplars consistently improve accuracy. Additionally, exemplar complexity is more significant than quantity. A single complex exemplar is more effective than multiple simple ones. Regarding candidate answers, RankPrompt demonstrates robustness to inconsistencies and minor benefits from using more candidates, though there are trade-offs with cost. These findings highlight the importance of exemplar selection and the robustness of RankPrompt in complex reasoning tasks. Figure 3 illustrates the performance of RankPrompt when using either correct or incorrect exemplars for ranking over 5 candidates. The results, obtained using GPT 3.5 Turbo, show that the use of incorrect exemplars significantly compromises performance, particularly in more challenging tasks like AQR80. Conversely, employing correct exemplars consistently improves accuracy compared to scenarios with no exemplars or inconsistent ones. This highlights the critical importance of exemplar correctness for the effectiveness of RankPrompt. Figure 4 illustrates the test accuracy of RankPrompt with varying complexity and numbers of comparison exemplars. The results are presented for GSM8K on the left and CSQA on the right, both using GPT 3.5 Turbo 16K. The key findings show that the complexity of exemplars is more significant than their quantity. Specifically, using a single complex exemplar yields better results than employing multiple simple exemplars. This observation underscores the importance of exemplar complexity in enhancing the accuracy of RankPrompt. Figure 5 illustrates the consistency rates of zero ranking and RankPrompt when ranking 5 candidates that are shuffled 3 times. The results, obtained using GPT-4, show that RankPrompt exhibits greater robustness with consistency rates ranging from 75% to 85%, compared to zero ranking. Figure 6 illustrates the test accuracy of different methods as the number of reasoning paths varies. The results are derived from the GSM-8K and CSQA test sets using the GPT 3.5 Turbo 16K model. COT prompting employs greedy decoding, whereas other methods utilize sampling with a temperature of 0.7. The figure highlights that both RankPrompt and majority voting show improved performance with more candidates, but the gains plateau beyond 5 reasoning paths. This suggests a trade-off between performance and cost, recommending the use of 5 candidates. In this study, the authors introduce RankPrompt, a method designed to optimize the output selection from a diverse set of reasoning paths generated by large language models, LLMs. This method offers 3 primary advantages. It eliminates the need for additional models or human annotations. It achieves strong performance across various reasoning and automatic evaluation tasks, and it is robust to inconsistent reasoning paths. The comprehensive evaluation highlights that the precision and complexity of comparison exemplars are critical for ranking performance. However, the study also acknowledges limitations, such as the reliance on proprietary language models, which creates barriers for researchers. Additionally, the use of comparison exemplars increases context size and API costs. Future work will focus on enhancing the ranking capabilities of open-source models and exploring methods to condense candidate paths to reduce costs. Table 6 presents the error statistics on the Aquarat dataset when using GPT 3.5 Turbo. The data reveals that RankPrompt produces 72 errors, while COT prompting accumulates 105 errors. The table categorizes errors into types such as calculation, wrong approach, misinterpretation, and logical error. Notably, RankPrompt significantly reduces errors caused by wrong approaches from 42 to 27 but is less effective in mitigating misinterpretation errors, reducing them from 17 to 14. Thank you for watching.